Welcome to the Deep Dive. Today, we're plunging into the unseen engines that power so much of our modern world. I'm talking about automation workflows. These aren't just simple scripts anymore. They're complex, stateful, mission-critical systems driving everything from, say, employee onboarding, financial transactions, even ML pipelines.
Yeah, they've really become like a competitive necessity for businesses.
Totally.
And our mission today is to give you a shortcut, a way to get truly well-informed on this. We've dug through the articles, the research, your notes, and pulled out the key insights.
Right, the distilled knowledge without you having to wade through everything.
Exactly.
So today's deep dive is all about building these sophisticated automation workflows on AWS. We're focusing on two really huge challenges: scalability and reliability.
And this stuff matters directly to you, the listener. It impacts operational efficiency, how fast you can get things to market, customer experience.
And when they break, big problems. Business disruption, data loss, compliance headaches, it gets serious fast.
Yeah, and the sources we looked at really argue that scalability and reliability, they aren't a trade-off. Not really. They come from deliberate architectural design.
So what's the core idea then, the thesis?
The thesis is basically build a decoupled, event-driven, observable system and do it using a carefully chosen set of AWS managed services. That's how you get both.
Okay, let's unpack that. Scalability first. When we talk about automation workflows scaling,
Right.
what does that actually mean? How does a system handle like a flood of tasks versus just a trickle?
Right. Good question. So scalability, fundamentally, it's the system's ability to adjust its resources, compute, storage, network to match demand without performance just tanking.
Adjusting dynamically.
Exactly. And what catches people out sometimes is thinking bigger is always better. Scaling up, making one server massive, that can actually introduce more risk.
How so? That feels counterintuitive.
Well, in the cloud, that one giant server becomes a single point of failure. If it goes down, your whole workload might go with it. Big blast radius.
Ah, okay. That makes sense. So if scaling up has limits and risks, what are the main ways we actually achieve scalability in the cloud?
There are really two main dimensions. First is vertical scaling up or down.
Like getting a bigger EC2 instance, more RAM, more CPU.
Exactly. Or boosting RDS storage or IOPS. It's simple for a quick boost, but you hit physical limits and you still have that single point of failure risk we just talked about.
Okay, so what's the alternative?
Horizontal scaling out or in. This is where you add more resources, not bigger ones.
So more EC2 instances in an auto-scaling group, or more containers.
Precisely. Or how AWS Lambda just automatically spins up more instances when needed. You're distributing the load across many smaller units.
And the sources really emphasize this horizontal approach.
Oh yeah, they call it the cornerstone of modern cloud architecture. It's not just about hitting huge numbers. It inherently builds in felt tolerance. If one small instance fails, the others keep going. Smaller blast radius.
That sounds incredibly powerful for automation. Now, something else the sources mentioned: elasticity versus scalability. People use them interchangeably, but they're different, right?
They are, and it's a really critical distinction. Scalability is the architectural capability to handle growth. You build it in.
Okay, the potential.
Right. Elasticity is the action, the real-time automatic implementation of that capability. It's the system actually grabbing and releasing resources on the fly, ideally without humans intervening.
So a good system is designed to scale, and it can actually do it automatically when needed. It's both.
Exactly. You need both for a truly well-architected cloud setup.
Okay, so that's handling demand. But what about the other side of the coin, reliability? Making sure the system actually works correctly, consistently. It's more than just uptime, isn't it?
Way more. Yeah, the sources, drawing heavily on the AWS well-architected framework, define reliability as the workload performing its intended function correctly and consistently when you expect it to.
Correctly and consistently?
Yes. It covers operation, testing, and crucially, recovery from failure. For automation, this means every single execution has to produce the right outcome. No silent failures, no corrupted data.
And the framework gives principles for achieving this. What are some key ones for automation?
Well, a big one is to automatically recover from failure. Don't just monitor CPU usage. Monitor business KPIs.
Like workflow completion rates.
Exactly, or error rates. And when those KPIs dip below a threshold, automated recovery should kick in, ideally before a human even gets an alert.
And you can't just assume recovery works. You have to test recovery procedures, right? Like actually break things on purpose.
Absolutely. Tools like AWS Fault Injection Service, FIS, let you simulate failures in availability zone going down, a dependency failing. You validate your recovery plan before a real disaster. It's crucial for building confidence.
Makes sense.
And, as we discussed, scaling horizontally inherently helps reliability too. Lots of small resources are less impacted by a single failure than one giant one.
Right, spreading the risk.
Plus, stop guessing capacity. Use monitoring to automatically adjust resources. Avoids failures from under-provisioning and saves money by avoiding over-provisioning.
And the last one seemed really important for automation. Manage change in automation.
Oh, huge. All infrastructure changes, code deployments, config tweaks, security groups should happen through automation. Infrastructure as code, IAC.
Like CloudFormation or Terraform?
Yes. For workflows, this is doubly vital. Your version control not just the infrastructure, but the workflow definition itself. Treating your step function state machine like code in DIT prevents accidental changes breaking a critical business process.
That brings up the shared responsibility model. AWS handles reliability of the cloud, but we handle it in the cloud. Can you clarify that a bit? It sometimes feels fuzzy.
You can feel fuzzy, yeah.
Yeah.
The idea is AWS provides the robust building blocks, the global infrastructure, the services themselves. That's reliability of the cloud. But you are responsible for how you use those blocks to build your application reliably. That's reliability in the cloud. So AWS makes sure EC2 as a service is reliable. But if you run your app on just one EC2 instance, that's on you if that instance fails. You need to design for resilience, like running across multiple availability zones.
So AWS gives you the reliable bricks, but you have to build the reliable house.
That's a good analogy.
Yeah.
It forces you to think about fault tolerance at every level.
Okay, so putting it all together, scalability and reliability. The sources say they're deeply intertwined, and the goal is reliable scalability. What does that mean in practice?
It means you can't optimize one without thinking about the other. A system that scales massively but drops 10% of requests. That's scaling failure, not success.
Right, easily.
And a super reliable system that can only handle a tiny load. Also useless when demand spikes. Every design choice impacts both. How does your compute handle state when it scales out quickly? Does your retry logic accidentally cause a retry storm under pressure?
So you need both. Reliably fast, reliably correct.
Precisely. It's a balancing act baked into the architecture.
Okay, so to build this reliably scalable system, we need to understand the components, the anatomy of these workflows. Let's use that employee onboarding example to make it concrete.
Good idea. So HR marks someone hired. That kicks off a whole chain of events, potentially over days.
Yeah.
Create a database record, provision IT accounts, email, SSO.
Enroll in training, notify the manager, ship a welcome kit.
Exactly. A complex, multi-step, potentially long-running process.
And most modern automation workflows, regardless of the specifics, share some core technical pieces, right? What's the starting point?
It always starts with an event trigger, the signal that kicks things off. A webhook, a message landing on a queue, a database change event. Something happens.
Got it. The trigger. Then
you have task execution. These are the individual work units. Create the DB record, provision the account, each step.
usually microservices, Lambda functions, or containers.
Typically, yeah. Independent units doing one thing well.
Okay, trigger, tasks. What else?
State management. This is critical. It's the workflow's memory, its brain. It tracks where each specific onboarding process is. What's done? What's next? Did the last step succeed or fail?
Because the tasks themselves are often stateless.
Exactly. Lambda functions especially. State management stitches them into a coherent, long-running process. It's also the trickiest part to get right.
And finally, data.
Right. Data persistence and consistency. Workflows read and write data, but what if it fails halfway? IT account created, but the DB record save failed. You get inconsistent state. This is where patterns like the Saga pattern become essential for managing transactions across multiple steps or services.
That leads to a big realization the source is stressed. These workflows are inherently distributed systems.
Absolutely. You have to shift your mindset from simple scripts to distributed systems thinking. Asynchronicity, network latency, partial failures where one bit is down but others aren't, idempotency.
Idempotency meaning if a task runs twice by accident, it doesn't mess things up.
Exactly. Crucial in distributed systems where things can get retried. It's a different ballgame than a single monolithic application.
Okay, so it's a distributed system challenge. Let's talk tools. The Architect's Toolkit on AWS, starting with the foundation. Event-driven architecture, EDA. Why is decoupling with events so vital?
Because tight coupling direct, synchronous calls between services is brittle. If service B is slow, service A waits, and things cascade. It's fragile.
Like a house of cards.
Kind of, yeah. EDA uses asynchronous communication via an event router. Service A just fires an event, like new hire created, and moves on. Downstream services listen and react when they can.
So they're decoupled. They don't need to know about each other directly.
Right. They can scale independently, fail independently, be updated independently. The event router acts like a shock absorber, buffering things. It's fundamental for resilience.
AWS has three main tools here: SQS, SNS, EventBridge. Let's start with SQS.
Okay, Amazon SQS, simple queue service. Think message queue, usually one-to-one delivery, though multiple consumers can pull. The key thing is durability messages stick around, up to 14 days.
So if the receiver is down, the message waits safely.
Exactly. Great for decoupling tasks, buffering work, ensuring jobs get processed reliably. It has features like dead letter queues for failed messages and FIFO for strict ordering if you need it.
Okay, durable queues. Then SNS.
Amazon SNS, simple notification service. Think pub subtopic, one-to-many fan-out. You publish a notification, and it goes to all subscribers. SMS, email, Lambda, SQS queues.
But it doesn't hold on to messages like XQS does.
Generally, no, not by itself. If
Yeah.
there are no subscribers or they can't receive it immediately, the message can be lost. So it's more for broadcasting, for transient notifications.
And the third one, EventBridge.
Amazon EventBridge. This is more of an event bus, many-to-many routing. It's really powerful for building sophisticated event-driven apps. It can route events from AWS services, your own apps, even SaaS partners.
And it has more features like filtering.
Yeah, advanced content-based filtering rules, schema registry, archiving, and replay. It's often the central nervous system for modern EDA on AWS. The sources pointed out something interesting, though. For critical steps within an automation workflow, sometimes using SQS between internal steps, even if it seems like overkill, provides that extra durability guarantee that nothing gets dropped silently.
Interesting. So even for internal handoffs, SQS might be safer sometimes.
Can be, yeah.
Yep.
Depends on criticality.
Okay, events are flowing. Now, the execution engine, the compute layer, this feels like a huge decision point. Lambda first.
Yeah, here's where it gets really interesting. The choice impacts operations, cost, control, a lot. AWS Lambda, the serverless compute, is often the best starting point.
Why?
It's event-driven, fits EDA perfectly, no servers to manage. It scales automatically, like instantly from 0 to thousands.
Yeah.
Perfect for the bursty, unpredictable traffic you often see in automation. Lowest operational overhead.
But it has limitations, right? The 15-minute timeout.
Yep. 15-minute max execution. Inherently stateless, so it needs external state management. And potential cold starts, though that's getting better and you can mitigate it.
So if a Lambda doesn't fit, containers.
Exactly. Containers give you more control. Good for longer running processes beyond 15 minutes, or stateful apps, or if you need specific OS libraries, maybe GPU access. Also a good path for migrating existing container apps.
And on AWS, that means ECS or EKS. How do you choose between them for automation?
Good question. Amazon ECS, Elastic Container Service, is the AWS native option. It's simpler, integrates really tightly with other AWS services, lower learning curve if you're already deep in AWS.
Okay, the simpler integrated option. And EKF.
Amazon EKS, Elastic Kubernetes Service. That's managed Kubernetes. More powerful, more flexible, part of that huge open source CNCF ecosystem, but also, frankly, more complex to manage.
So you choose EKS.
If your team already knows Kubernetes really well, or you need specific tools from the K8's ecosystem, or you're aiming for multi-cloud or hybrid deployments where Kubernetes provides portability, the advice generally is start with Lambda, look at ECS if Lambda doesn't fit, and only go to EKS if you have a clear, compelling reason for that extra complexity.
Lambda first, then ECS, then EKS.
Got it. So we have tasks running in Lambda or containers, but they're often stateless. How do we manage the overall workflow, track progress across potentially days, like that onboarding example, that state management problem?
Right, that's where the conductor comes in. AWS step functions. You've hit on the core challenge. Business processes are stateful, but our modern compute building blocks are often stateless. Step functions bridges that gap.
It's the workflow's brain, keeping track.
Precisely. It's a serverless orchestration service. You define your workflow visually or as code as a state machine. Step functions then manages the state, sequences the tasks, handles errors, retries, parallel steps, all that complex logic.
So it separates the how from the what. Beautifully put, yeah. The orchestration logic, how, is in step functions. The business logic is in your Lambdas or containers. It provides durability and visibility into the whole process.
And there are two types, standard and express.
Correct. Standard workflows are the workhorses for long-running processes, up to a year. They're durable, auditable, and offer an exactly once execution model.
Exactly. Once is vital for things like payments, right? Can't run twice.
Absolutely. Or our onboarding example. You don't want two IT accounts created. Standard is for those mission-critical, non-idempotent tasks.
And Express.
Express workflows are for high-volume, short-duration stuff up to 5 minutes. They're much cheaper at scale, but offer at least once execution.
So, okay, for tasks that are safe to run more than once, idempotent tasks.
Exactly. Think high-throughput data processing, IoT ingestion, simple transformations. And if you need even longer than a year, you can use a parent standard workflow to launch child standard workflows.
Yeah.
Virtually unlimited duration.
Wow, okay. Powerful stuff. Last toolkit piece. Data persistence to memory. RDS versus DynamoDB seems like the main decision.
Often, yeah. For structured data needing strong consistency, ACID, and complex queries joins, aggregations, Amazon RDS is the choice. Think the final employee record database. Manage PostgreSQL, MySQL, etc.
The traditional relational database managed.
Right. But for many operational tasks within the workflow itself, tracking state, history, high-volume reads-writes with low latency, Amazon DynamoDB often shines.
The NoSQL option.
Yep, fully managed NoSQL. Excels at massive scale, consistent single-digit millisecond latency for key-value lookups, flexible schema, often more scalable and cost-effective for those simple, high-velocity operational data patterns common in workflows.
Now, consistency across these distributed steps. So we mentioned the saga pattern. How does that actually work, and why is it so important here?
Right, you can't just wrap everything in one big database transaction when you have multiple services, maybe multiple databases. A saga is a sequence of local transactions. Step 1 does its database work, then triggers Step 2. Step 2 does its work, triggers Step 3.
Okay, a chain of local transactions.
But what if Step 3 fails? The saga pattern includes compensating transactions. Step 2 has a way to undo its work. Step 1 has a way to undo its work. So if failure happens, the saga triggers these compensating actions to roll things back, maintaining overall consistency.
That sounds complex to manage manually.
Incredibly complex. This is where, as the sources stress, step functions is a lifesaver. It can orchestrate this saga pattern for you, managing the forward steps and triggering the correct compensating actions on failure. It handles the state tracking and error handling that makes sagas feasible in practice. It basically simulates a distributed transaction.
Okay, that's huge. So looking back at the toolkit, EDA, Lambda containers, step functions, RDS DynamoDB, it feels like they all reinforce each other.
Absolutely. It's like an architectural flywheel. Want scale and reliability. Go. Event-driven. Event-driven. Lambda fits perfectly. Lambda stateless. Needs step functions for orchestration. High-volume state tracking. DynamoDB fits well. Each choice makes the next one more logical, creating this cohesive, resilient system.
Makes sense. But a great design isn't enough. You need solid operational practices for production. What are the essentials?
Number 1, build with blueprints. Infrastructure as code, IAC. CloudFormation, Terraform. Define everything in code.
Why is that so critical?
Avoids manual errors. Makes changes repeatable, reviewable, auditable. The sources push for a GitOps workflow. Git repos the source of truth. Changes via pull requests. CI/CD pipeline deploys. Safe, predictable changes.
Okay, IAC is foundational. What about security, network isolation?
Crucial. Amazon VPC design. Use public and private subnets. Put your core logical lambdas, containers, databases, and private subnets. Massively reduces the attack surface.
So they can't be reached directly from the internet.
Right. And use VPC endpoints to talk to public AWS services like S3 or Textract without going over the public internet. More secure, potentially cheaper.
And controlling permissions, IAM.
Principle of least privilege with AWS IAM. Non-negotiable. Give every component user, Lambda container, only the minimum permissions it needs to do its job. Use fine-grained IAM roles, never hard-code keys, use roles for temporary credentials, limits the damage if something gets compromised.
Basic security hygiene, but essential. Finally, observability. In these complex distributed workflows, how do you figure out what's going on, especially when things go wrong?
Yeah, traditional debugging just doesn't work well. You need observability, the ability to ask questions about your system's state from its outputs. It stands on 3 pillars.
Pillar 1, logging.
Logging, yeah. Use Amazon CloudWatch logs. Emit structured logs, like JSON, from your Lambdas and containers. Then you can use CloudWatch logs insights to query across everything effectively. Find that needle in the haystack.
Pillar 2, metric.
Metrics with Amazon CloudWatch metrics. Track key performance and health indicators.
Yeah.
Lambda errors, queue depths, workflow execution times. Set CloudWatch alarms on these metrics to get notified or trigger automation when things go wrong. Your early warning system.
And the third pillar, tracing.
Tracing with AWS X-Ray. This one's a game changer for distributed systems. You enable it, and it follows requests as they jump between services, API gateway, Lambda, step functions, etc.
It maps the whole journey.
Exactly. It generates a service map showing connections, latency at each hop, error rates. If a workflow is slow or failing, X-Ray points you right to the bottleneck or the source of the error, turns hours of debugging guesswork into minutes. It's like an MRI for your workflow.
Okay, theory and tools are great. Let's make it real. Walk us through that example. The document processing workflow with human approval. User uploads an invoice PDF.
Right. Let's build it using these principles. Step 1, scalable ingestion. The web app gets a pre-signed URL from your backend. The user uploads the PDF directly to an S3 bucket using that URL.
So the upload bypasses our application servers. Smart.
Totally. Scales massively. Then S3 emits an S3.object-created event when the upload finishes. That event goes to a custom Amazon EventBridge event bus.
Why EventBridge?
Flexible routing. We can easily add other rules later. For now, one rule matches PDF uploads and targets.
The orchestrator.
Exactly. An AWS step functions standard workflow. Standard because it might wait days for approval, needs to be auditable, and we want exactly one semantics for processing invoices.
Okay, the step function kicks off. What happens inside?
First step inside the state machine, an extract text task state. It invokes a Lambda function.
What does Lambda do?
Downloads a PDF from S3, calls Amazon TextRack to perform OCR, and extract the data, like invoice number, date, amount. It passes that structured data as output.
Got the data. Then the approval logic.
Next, a check invoice amount choice state. It looks at the extracted amount. If it's, say, over $10,000, it branches to the approval path. If not, it skips straight to processing.
Okay, let's say it's over $10. Approval needed. What now?
It enters a wait for approval state. This uses a need step functions pattern, a parallel state combined with a task timer or callback.
How does that work?
Inside the parallel state, one branch, Notify Manager, might publish a message to an SNS topic. The manager gets an email with approve reject links and a unique task token generated by step functions.
Okay, manager notified.
The other branch uses a task state configured with the wait for task token integration pattern. This pauses the workflow indefinitely, consuming almost no resources.
Paused until when?
Until the manager clicks approve or reject. Those links hit an API gateway endpoint, which triggers another Lambda. That Lambda calls the step function's API, send task success or send task failure, using the task token. That resumes the workflow.
Clever. Very efficient way to handle human interaction. So once it's approved, or if it skipped approval.
It proceeds to a process invoice task state. Another Lambda function takes the validated invoice data and writes it into an Amazon DynamoDB table.
Why DynamoDB here?
Good fit for the operational data. High volume writes need low latency. Simple key-based lookups for invoice status. Scales well? Then the workflow finishes in a clear success or fail state.
How do we make this robust? Error handling.
Built-in retries and step functions for Lambda invocations handle transient issues, exponential backoff, jitter, standard best practices. But critically, dead letter queues, DLQs.
On the step function itself, and maybe the lambdas.
Yes, configure a DLQ and SQS queue for the state machine. If a task fails permanently after all retries, the failed execution context goes to the DLQ. This prevents data loss. You can inspect it, maybe manually retry later. I saw a project once skip DLQs on a critical workflow. Big mistake when a dependency failed. Messages just vanish. DLQs are your safety net.
Good lesson. And security for this whole setup.
VPC first. Everything inside. Lambdas, DynamoDB table, and private subnets. No direct internet access. Communication with S3, TextRack via VPC endpoints. Traffic stays within the AWS network. And every component gets a minimal IAM role. Least privilege throughout.
Security baked in. And observability.
AWS X-Ray, enabled end-to-end. API gateway, Lambdas, step functions. See the whole flow. Structured CloudWatch logs from Lambdas. Custom CloudWatch metrics for key business indicators, invoices processed, approval times, with alarms. Full visibility.
That example really pulls it all together. It shows how these managed services compose into something scalable and reliable.
Exactly. So to recap the big picture.
Yeah.
Building modern automation backends. It's distributed systems design. You succeed by embracing decoupling event-driven patterns.
Which leads naturally to serverless compute like Lambda where possible.
Right, reserving containers for specific needs. externalizing state management to step functions, choosing the right database, maybe RDS for complex relational data, DynamoDB for operational scale.
And using patterns like Saga, likely orchestrated by step functions, for consistency.
You got it. It's about picking the right tool for the job from that AWS toolkit.
And looking ahead, this kind of architecture seems really flexible, right? Ready for more intelligence.
Definitely. The future is automated and composable. Because it's event-driven and uses microservices, you can easily add new steps. Deploy a new service that listens for an existing event. Maybe add an AML step for intelligent classification or fraud detection. Make automation smarter, not just faster.
So the final thought for our listeners.
I think it's this. Architecting for scale and reliability on the cloud isn't about finding one magic service. It's about understanding the core principles, decoupling, events, state management, fault tolerance, and then skillfully using the combination of AWS services, like the ones we discussed, to build a system that's powerful, resilient, elastic, secure, and actually solves the business problem you needed to automate.